Good afternoon and welcome again to another MEscope webinar. My name is Mark Richardson, the Marketing Manager for Vibrant Technology, and as usual, I'm joined by my father, Mark Sr., the CEO and founder of Vibrant, and also Brian Shores, the Director of Applications, will be joining us as well. Today's webinar is, today's topic for a webinar today is a comparison of video ODSs with an iPhone. So you may or may not know that you can you can pull ODSs from a video, and as well with an iPhone. You do not need to go out and spend an exorbitant amount on a high-speed camera. So we will show you some examples today of that. Before we get going, just a couple of housekeeping items. We will be recording this webinar, so I'll be uploading this to our YouTube channel, usually first part of next week. In addition, I can send out a PDF version. We've gotten a lot of requests for that recently. So we will send out a PDF version to all attendees as well, so you can share that with your colleagues who may not be able to join us. If you have questions, we will answer your questions at the tail end of the webinar. We will keep everybody on mute until then, but if you do have questions, feel free to type your questions into the dialog box there in the GoToWebinar panel on the right side of your screen. With that, let me hand things over. Dad, you take it away from here.
All right, well, welcome to all of you. It's still morning time. I'm here in Southern California. The Vibrant office is in Centennial, but we are all working remotely, except for the office manager who goes in to get the mail. And so the rest of us are using internet technology to communicate with each other. Okay, so I wanted to get the animation going. Let's go through some slides first. I'm going to go through a number of slides and introduce the topic of cell phone videos and how we extract an ODS, or an operating reflection shape, from a video. This is a relatively new technology. We've had it in MEscope now for about 4 years. There's a couple of other competitors worldwide that are doing similar things with videos. As Mark mentioned, you can spend more money and buy a higher speed camera. Typically, you'll need lighting and so forth, but everybody owns a cell phone, so you can really get started with a cell phone. And so we'll talk about that as we go through. Advantages. Most vibration occurs too quickly and displacements are very small, or both. So we need some special software to extract vibration, like you're seeing on the screen here, from a video. We use the term video ODS, and we've trademarked it because what you're looking at is actually an animation created in MEscope once the data has been extracted from the video. So we're just using animation in MEscope that's been in there for years. We call it a photo model, and now we're just animating frames of a video with the data that's been extracted. And that allows you to see, we can amplify the motion, we can slow it down, we can look at different speeds, different machine orders, curve fit the data, get mode shapes out of it. We're not going to do all that today. This talk is actually the beginning of a talk I'm going to give next week at the Vibration Institute in Niagara Falls, New York, where the title of that talk is the comparison of video ODS data with accelerometer-based data. So we'll talk a little bit about that as we go on, because accelerometers are still used for machinery health monitoring, structural health monitoring, walk around data collection, troubleshooting, modal analysis. All these different things are still rely on accelerometers, and they're not going to go away. They have definite benefits, but as a quick look of what's going on, we can take a video during normal operation. So that's what I've done here to look at the video ODS data that we extract from videos from a cell phone that were recorded at 4 different speeds or recording rates. But here's an advantage. I mean, we can't shut down the machine to do an ODS or a careful modal test for resonance analysis. But these videos that we can extract very quickly from a cell phone video, load it into a computer, and get an animation that looks something like this. We'll start to see things that are going on that perhaps we didn't even anticipate. So we're going to talk a lot about the term ODS, which stands for operating deflection shape. So as soon as I take data on 2 or more points on the surface of a structure, I can now talk about a shape because I have motion of one point relative to another. The advantage of a cell phone and a video camera, more expensive camera, we also resell a more expensive, higher speed camera at Vibrant, and that's on our website if you're interested. But the pixels in the cell phone video are simultaneously sampled. Now, that's not exactly true because it's a raster scan, but Brian Schwartz has done some testing, some research. I think, Brian, maybe you can chime in here. The difference between the top of the screen and the bottom of the screen is maybe 4 degrees difference, which in an ODS like this, you can't tell the difference. Go ahead.
Yeah, with the cell phones, you do have, it does scan through the pixels rather than acquiring all the pixels simultaneously like in the high-speed camera. And because of that, there is a time lag between the first pixel acquired and the last pixel acquired. That time lag, the length of time is a 32,000th of a second, and that ends up being about 4 degrees of error at the highest
between the top and the bottom. Yeah.
Right, but between the top and the bottom, first pixel and last pixel acquired.
Right. Well, let's go on, and I'll mention this in another slide. This technology is evolving. Cell phone videos are a popular technology. It's just going to get better and faster and more accurate as time goes on. But here's a quick look at something called softfoot. You know, the mounting of this machine is actually coming away from the concrete floor or whatever the floor is that it's been bolted down to. So this is a common problem with machinery where it's been mounted on a weak foundation. The contractor didn't do a good job of installing it to begin with, or over time the bolts loosen up, and this is a very common problem with anything that's been mounted. Machines, pumps, motors, gearboxes. Here's a more complicated machine. Now, once we've extracted the vibration data, this is another thing we can do in MEscope. We can actually put the magnitude in phase. We can differentiate the data, which is normally displacement data. So now this data is being displayed in inches per second. So that's a common parameter that machinery maintenance people use to determine high vibration level. Anything over an inch per second is probably going to come loose pretty soon. So we can do that right on the animated picture from the extracted data. But here we're talking about other advantages. Why use a video ODS? We can remotely capture vibration, hot and dangerous machinery, so we don't have to be putting accelerometers on the surface. But if we want to instrument the machinery to do a more careful modal analysis or resonance analysis, we can see from the video where to put the accelerometers. We are using an algorithm in MEscope that's commercially available, and our competitors have either developed algorithms of their own, or they're using one from MIT, which was released years ago, worked on by students in the graduate school. So there's a number of algorithms, but these extraction algorithms are being used for autonomous driving of cars, robotic vision, and drones. So the technology is being utilized in a lot of different applications now. And as I said, it's going to just get better as time goes on. The other advantage of extracting time waveforms from a video is that we can use all the normal signal processing methods that we use with accelerometer data that's been digitized from accelerometers. We can do time domain windowing, the Hanning window. I'll show you some results here in a minute. We can do spectrum averaging to remove noise, and we can measure these common frequency domain functions. A DFT, which is, most people just call it a Fourier transform. The Fourier transform is the algorithm that converts a time waveform into its digital Fourier spectrum. So if we're going to look at an ODS, we collect a whole bunch of these. Auto and cross spectrum, very popular. Most analyzers will calculate those, so you can look at the auto spectrum of a vibration signal. FRF, this is normally frequency response function, normally used for modal, where we do curve fitting. And then the coherences come along with the FRF calculation that tell us whether the input, the force that we measure, is related to the response that we measure. So that's a common, these two typically are a pair of measurements made in FFT analyzers, and digital signal acquisition systems. We can do this stuff in MEscope also. We're going to talk mainly about what we call ODS-FRFs at Vibrant, because those measurements allow us to integrate, differentiate, to get velocity of an ODS from the measurement. They're frequency domain measurements. They have peaks in them, just like an auto spectrum. In fact, the quick way to explain an ODS-FRF is that it's a combination of an auto and a cross spectrum. It's the auto spectrum of each response. Now, in the case of a video like this, we'll see there's a whole bunch of points here where we get the response at each point on a grid behind the picture, and combine the auto spectrum with the phase of the response relative to what we call a reference response. So that's typically the way you make an auto spectrum measurement anyway. You would take a reference and you multiply the DFT of the reference by the conjugate of the roving. So that's what an ODS-FRF is. We'll talk about that more as we go here. Why use a cell phone? Everyone has it in their pocket. It's low cost. It's non-contacting. So we can get vibration, animated, amplified, slow motion vibration like this from a video recording. Now we're going to look at the 4 different recording rates that I have in my cell phone. And this data that we're going to look at here in a minute is data that I took. I'm not even very good at using my cell phone. And so we'll talk about some of the problems that you may encounter when you do make a cell phone video and then load it into your computer and post-process it in MEscope. However, I can handle machinery all the way up to 7,200 RPM, sampling at the highest. The FPS is called frames per second. That's the same as the sampling rate we use in an analyzer to analyze the data. And then the spectrum, or in this case, the RPM range that I can analyze is 1/2 of 60 RPM times cycles per second. So 30 cycles per second would be a sampling rate of 1,800 RPM, take half of that for the spectrum. And the other issue that needs to be kept in mind when we take video data is that there is no anti-aliasing filter like there is in an analyzer and a data acquisition system. And what the filter is for is to filter out any higher frequencies that will show up in the spectrum. So we'll see in the example that I am going to go through here in a few minutes that the machine is running at over 900 RPM. It's actually running at 1450 RPM that I took the video on. But that resonance or that running speed, we call it an order, a peak in the data, actually shows up exactly where it should because it's aliased around the 900 RPM. We'll get into that in a minute. Here's some other advantages of a cell phone that don't exist. I already mentioned this with a high-speed camera. You need artificial lighting with a high-speed camera. A cell phone they have algorithms in these phones that will brighten up the picture so that even in a dark place, a machine like this in a dark place, you get usable data that you can extract vibration from. So artificial lighting and jitter removal, we have capability in MEscope. I've been through it. I'll explain a little bit of it to you for removing background, what we call removing background motion, and then just end up with the motion of the test article. Here's another reason why ODS-FRFs we prefer to use them in MEscope for looking at vibration. An ODS-FRF, unlike a cross spectrum or an FRF, can be integrated and differentiated. So I can take the data from my video and it will have units of displacement. I can differentiate that data and get velocity units, either on my ODS-FRF data directly or on the ODS that I extract from, let's say, a resonance peak or an operating frequency peak in the ODS-FRF. And then in the same manner, I can take ODS-FRFs that I've calculated from accelerometers and integrate them. So now I can compare a direct comparison in velocity units of the accelerometer with the video. How do we compare ODS? In MEscope, there's two ways to numerically compare two shapes. And when we talk about an operating deflection shape, this works for mode shapes and operating deflection shapes. When we make measurements on any machine or structure, doesn't matter what it is, as soon as we make the second measurement on the surface of the machine, either with a video or with an accelerometer, we have an operating deflection shape. So our experimental data is in fact an operating deflection shape at each moment in time and at each frequency of the DFT that we calculate from the time records. So we'll see that in a minute. Modal assurance criterion was the PhD thesis of a professor at University of Cincinnati. His name is Randy Alamain. He discovered this mathematics. It's intriguing. It's very simple. It's actually a curve fit of shape A to shape B multiplied by a curve fit of shape B to shape A. And when you do that with a little bit of complex math, because these shapes have magnitude and phase in them, you end up with a Mach value. And so what the Mach measures is the collinearity between two shapes. meaning that they lie on the same straight line. So in this picture here, we got a straight line of one shape. Shape A has got values of 1 and 1 in it. So it's out here at coordinates 1 and 1 on this top view. And then down here in the 3D view, same thing. So all along this line here, that's just a straight line that goes through the origin and also 0.11, if I compare that with a shape B that has different values in it, and here we've just ranged the values from -3 to +3 of X and Y to get this surface. You can see that when the two shapes are quite different from another, then MAC equals 0. But if they lie along the same straight line, meaning they're collinear, then MAC is 1. It doesn't matter what their values are in the shape B versus shape A. Here's one that we invented at Vibrant. We use it for a number of different things. It's unique to MEscope. We call it the shape difference indicator, and it actually computes a value between 0 and 1 also, just like MAC. But it's based on the difference between two shapes. So here's a little surface of SDI and then a top view over on the right. And again, the red area is where the two shapes are numerically very different from one another. And there's only two places where their SDI value will be equal to 1. So if they vary by just a little bit from one to the other, numerically speaking, they're different. They got different numbers in them, both magnitude and phase. Okay, so here is we're gonna go look at this in MEscope in a minute, but here's kind of something to talk about. Here's what we call a animation of a pair from two sources. So over on the right, we've got two ODS-FRFs. Here's one from the 30 FPS video, and there's 10 of them in there, and they're selected. So it's saying right here, number of selected measurements, impounds is our version of measurement. There's 10 of them. There it is, there's an aliased peak at 340 RPM. We'll go in and look at this in more detail. The actual speed of the machine was 1460. That's what this one says. And this was taken at 60 frames per second. So it has a bandwidth up to 1800 RPM. And sure enough, the 1460 RPM first order running speed peak is showing up. These other peaks are higher frequency orders that have been aliased down to lower speeds. Those aren't really the speeds of the machine. You got to be a little careful when you use videos. The other thing now is on the animated picture, we're only going to look at 5 points, a point on the top of each bearing block, and then a point down here. You can kind of see the 3 locations where we've glued down some metal washers, iron washers to the aluminum surface so we can use a magnet with an accelerometer. And as I mentioned, this is all in preparation for a comparison between accelerometers and videos. But what's interesting here is that the Y motion, and we'll see that in a minute when we amplify it in MEscope, this is almost like a mass on a spring. There's a little bit of an unbalance on this outer rotor. We put that in there purposely just to make the machine vibrate at 1450 RPM. And it's bouncing up like a mass on a spring because it's got rubber mounts underneath of it, and it's sitting on a table. So you can see the phases here of the ODS value in the Y direction. They're all relatively the same, just looking at the little phase diagram. And the displacements are in mils. Let's not worry about that. What MAC is telling us is that the ODS from this 30 frames per second versus the 60 frames per second, the ODSs are 80% alike. Now we saw in the previous slide where, you know, ODS should be, or max should be above 90%, just a rule of thumb. And when it's above 90%, then the two shapes are almost the same. Less than 90%, they're linearly independent, meaning that they don't lie on the same line with each other anymore. But this is showing that the MAC value is between these two shapes is 80%, and then the SDI value is very low, meaning that numerically they're different. So if you look at the magnitudes of some of these points here, they're quite different between the two videos. Okay, here's the second example then we're going to look at, and this is between the 60 frames per second and the 120 frames per second video. And then over here are the ODS-FRF. Again, this is the 60 now. Down here's the 120. So 120 is showing up nice and clear as 1458. Up here we got 1464. The resolution of these measurements depends on the length, the time period of the video, the time length, not the sampling, the time length. So if I take 10 seconds of data, divide 60 by 10, that gives me a resolution of 6 RPM between samples. If I take 20 seconds of data, that cuts it down to 3 RPM. So I don't know what these are right here. We'll look at them in a minute. But what we're looking at are 10 selected out of over 11,000 measurements from this video over here, and down here we got 12,000 measurements from this video. So a lot of measurements. There's millions of pixels in each frame of these videos, and we're not showing the data at every pixel. We're showing it on a grid of points. So a little different, little unique to MEscope, where we animate the picture or the frames of the video on a grid, a rectangular grid of points. So we'll look at that in a minute. Here's the final case, 120 versus 240. This is the highest sampling rate that you can get in your cell phone. And you can see now, I've got the order cursor turned on here, and you can see the first 4 orders of this machine. And these other peaks in here could be aliased higher frequency orders. We'd have to go in and look at that. We actually have software in MEscope where we can unfold the frequency spectrum from, in this case, it would be 7,200 RPM all the way out to 14,000 RPM and lay those aliased peaks out where they belong. So we can do that with order data, but we're not going to do that here today. That's just something else that we've developed in MEscope for, again, working with aliased data, which is a problem we have with any video. But again, here, if we look at the phase angles, they're very similar, at least in the Y direction. And for each video, they're very consistent. And what that means is that in the Y direction, the vertical direction, this machine is just hopping up and down on its rubber mounts. Mac is not very good though. So comparing this data to this data, they're not as collinear, although the SDI is a little better now, 30%, 31%, but still different values. Now what we're going to do is actually extract the ODS data from the ODS-FRF measurements. And here, I've already been talking about this peak here at basically 340 RPM is aliased. And so when we do the integration from mils to inches per second, or differentiation, sorry, we have to have the correct frequency of the shape, in this case, the order. So here we're going to have a shape, an ODS, magnitude and phase in it. And we're going to do something else here, which is, again, part of MEscope, we can actually take one or more shapes and curve fit them. It's just a linear least squares curve fit of those shapes to ODS data. So in this case, what we're going to do is take one ODS, curve fit it to the other. The reason for that is that each of these sets of data have a different reference, and we just pick a point on the video anywhere. You know, stop the video, pick a frame, and pick a point on the grid and call that our reference. We need that for a cross spectrum or an ODS-FRF so that we get the correct magnitude and phase in all the elements of our ODS. So that's just something to think about. If I can calculate the phase between all of my responses and a reference, then all the phases relative to each other are correct. However, they're going to be different based on the phase of the reference response. So a lot of words, but that's why we do this curve fitting, to make these two shapes a little more collinear. And in fact, they're very collinear, because over here on this picture, this is actually a value of 1. The MAC value is a value of 1. SDI is still very low. Again, after we've done the curve fitting, and we can differentiate to inches per second, comparing, this is the 60 FPS to the 120. Again, MAC value, they're basically getting the same answer. And that is corrected for the phase primarily. Down here, magnitudes are still not good. Okay, well, here's in the third case, the 120 to the 240, MAC is correct. We've corrected the phase by curve fitting the shape A to shape B, and the shape difference is 61%, so that's pretty good. Oh, well, here's a case where I took the second order. See, now I got extra orders in these higher frequency spectra. So 120 versus 240, but if you go to the second order, it's actually at 2900 RPM. So I put the peak cursor there and extract that data, and then down here at 2900 and 16, a little bit different, again, based on the resolution. Those match up very well. So the second orders match up even better. 83%, not quite to our 90% threshold, but much better. Okay, this is the conclusion. We can come back to this and wrap it up with that. Let's put this down. And now I've got a video up here. I'm just going to play this video. Okay, there's a, I don't know whether you can hear that. I'm going to turn the noise down a little bit, because the iPhone actually records the sound along with the video. So here it is. You can see there's a little bit of motion. This is the raw video. You can't tell anything else that's going on here. But you can see the wheel rotating. You can actually see the little screw that we put in here to give it a little bit unbalanced so it would vibrate. The other thing is that you can go into this. This is the properties of the video, and you can see that the actual frame rate is a little bit under 30 frames per second. So, and then this is the resolution. This is the number of pixels per. So, 1 million pixels per frame in the video. And so the cell phones are amazing. They have a lot of memory, so they can record stuff like this. All right, let's go into MEscope and process this video. I'll take you through how we process it. We'll just do it for one. And let me just put this up here, and I'm going to go over here under videos. And we call this our video ODS wizard. So I'm going to open that, and I'm going to go to the desktop, and here's that video we just looked at. So now it's in MEscope in what we call our wizard, and you can see over here on the left, a number of steps that we go through to process this video in order to extract the vibration from it. So the first thing we can do is get rid of a whole bunch of this picture because we don't really care about anything except the test article, the machine itself. So this is typical of what you do with a cell phone camera. You take a picture of a machine, but you're only interested in part of it, the machine itself, not the rest of the video. So get rid of all those pixels, and we're just going to focus on this much of each frame. Now I can adjust brightness and contrast. If I'm using a high-speed camera, this is very helpful because changing the contrast just makes the algorithm work better, because now I can see the difference. The way the algorithm works is it looks for a difference between frame to frame to frame of where that pixel moved to. And if it's all the same color, like right here where it's all black, well, the algorithm can't do much with that part of the frame to frame, because it all looks the same. So it really helps to brighten things up. We can brighten them up or increase the contrast. So brighten them up, I don't want to do that. That's going to over brighten it. But with cell phones, you really don't have to worry so much. The camera itself in the cell phone does a good job. Okay, so here's where I set the frames per second. Now this is set to 60. I'm going to put in 30. And that's telling me that in this range of the videos, the frames, I've got 10 seconds of data. So I'm going to get about 6 RPM of resolution. Up here it's showing me the first frame and the last frame. If I draw these all the way to the edges, this video actually has 30 seconds of data in it, and it's got 926 frames of data, or samples in the time domain. When we extract the video, we're going to end up with time waveforms that have 926 time samples. But let's just set it back to something a little smaller. We're not really going to do much with this because we've already got the ODS-FRFs. But if we're going to calculate ODS-FRFs, we should have at least this much data. Okay, so let's just go on and go to the next step. Here's the point grid I was talking about. And this is the rectangular grid of points in MEscope in the structure window, just like any other 3D model, but this is a 2D model of a two-dimensional point grid, and it's got 12,000 points in it. That's kind of the default. I don't necessarily need that much resolution. I like to go with 4,000 to 8,000 points. It speeds up the processing a little bit. You can go back into the wizard and change the number of grid points. That's real easy to do. Go back and forth, getting used to how MEscope does things. And now we're going to extract the time waveforms. So I just clicked on that. It's going to take 40 seconds, 38 seconds. So pretty quick with a video like this. Now, when we get to the higher speed videos, they typically have a lot more frames in them. And again, if I don't crop the video and I just take the whole video with all the background in it, it's going to take longer. I mean, it can take a few minutes to do a video. We're not going to go through all 4 different sample rates. I just want to show you how quickly we can process a video and get some results to work with. Okay, here's where if we want scaled data, now we can skip this step if we want, but what we want to do is pick 2 points on the test article and then enter a true dimension for those 2 points. And we want to pick something that's in the frame of the video itself, in the 2-dimensional space of the video. I don't want to pick a point way in the back here and then one in the front, and then put in the true dimension of those 2 points, because that's not what the video recorded. But here we know I can just take a ruler, and the front of the machine is about 15.5 inches. In fact, it's pretty much exactly that. So that's going to scale our time data and our frequency data to displacement. In this case, we're using inches, but we can convert from one to the other. MEscope allows you to change your engineering units to anything you want. But once you've got a scaled set of data, then you're going to get some good results. Now here, look up here on the picture, you can see that a whole bunch of the points have already been removed from the grid, because those points, and that's because my little slider bar here, now they're all included. There's all the points. But if I slide this over, this histogram is ordering all my motion that I've extracted according to magnitude. So I don't necessarily want all these points that are up here in the, open space where there's nothing going on. So I can interactively move this histogram over and get rid of all these points, and you can just watch them as they get removed. So this, again, helps the analysis. I don't care about all those points. Let's just take those out of the analysis, and we're only going to work with the points on the test article that are important to us. I can draw the high side down, and that will take, if I got some points that are just flying around in the video, some loose pipe or some loose whatever, I can drag this down, and let me just pull it all the way down here and show you what happens. Okay, so that took out some high velocity or high magnitude, not necessarily velocity, but high magnitude. So I lost a few points in here. It looks like I lost a whole bunch of points around the edge. I don't care about those, so I can go ahead and just use the points that are left in the grid. You can see some of these over here. Now those are, the video will pick up stuff that you just don't want to deal with. Don't need to. All I care about is the machine itself. So it's going to finish, and now it's going to come up in MEscope, and it's doing a sweep animation, and there it is. It's showing an amplified picture in the time domain. It's sweeping through the time domain. This is in inches, and you can see the numbers are very small. But you can see this thing is just hopping around. If I go down here and click down here, here is the motion at 340 RPM. And it's a sinusoidal motion. And if I crank up the amplitude here, let's just go to animate amplitude. It's at 4. Let's set it at, I don't know. Let's set it at 20. See what that does. Well, that's a little too high. Let's go with an amplitude of maybe 10. So now you can see clearly what it's extracted. The bottom of this machine is just like a mass on a spring. Now, all this is exaggerated because I cranked the amplitude way up, but I don't really care about this pulley. We saw the pulley moving a little bit in the raw video. What I really care about is the motion of the two bearing blocks and the motion of the base plate. So those are where I can put accelerometers and compare answers. The rest of it was just recorded by the video, but if I was really interested in, you can almost see a little bit of a mode shape here coming out at being dominated, or let's say dominating the motion, the vibration of this rotor. And that's true. I mean, I've done experiments on other rotor kits where you can see the mode shapes as you go up in the orders. You can see all the mode shapes being dominating or contributing to each order. Okay, what else to say? Let me put this back over here. Again, this is, if I go down here and look at the I mean, this came out just really nice. I can integrate this data. Well, let's just go ahead and look at some of our other data that's in this project. So I'm going to go here to what are called hotkeys. Now I've got a bunch of hotkeys, and these, let me just show you one real quickly. This hotkey is going to compare the 30 versus the 60 frames per second. And a script, which is what the hotkey executes, you can see it's just going to take a structure window called 30 FPS, and it's going to do a whole bunch of things. It's going to animate a pair of shapes, and if I click on that, it's going to compare them with 60. So a lot of information here. This is a standard feature in MEscope. Let me just press that hotkey, and let's just take a look at what it's given us here. So this is my process of data between 30 FPS and 60 FPS. So already up. We saw earlier 10 of the points. So I can go into my model, any one of them, and pick out the 5 points I'm interested in. And the video, we extracted X and Y from each point. So if I come over here and just look at this data here, this is the ODS-FRF data. There's some of them are selected. That's all that I'm animating. But if I scroll down here to the bottom, this is what we call an envelope. So this is valuable because I've got how many in here? I've got 21,000 measurements, including the envelope here at the end. So this is one of the features in MEscope that we really need, because a lot of these measurements, they're ordered now according to their amplitude, but a lot of them don't have much in them. So this will show us, this envelope will show us what's in all of our data. And this set down here has got 11,000 measurements in it. So a lot of information. Now I can go and animate these. We already saw that for the 30 FPS that we just processed. But here's the results that we saw in the PowerPoint presentations. I can go up here and go under deflection. I can turn on magnitude and phase for these points. So this is what we saw in the PowerPoint. So this is another thing, that a feature you want to use as soon as you get some data to just kind of see how things are moving around. We already got the point labels up, so I can turn that off and clean that up a little bit. I can go back here and turn off the deflection, and that way we can look at these more carefully. Okay, well, let's go to the next hotkey. This is 60 versus 120 frames per second. We'll just take a quick look at what's going on between these two. Again, it's a comparison animation. And we saw in the video that the MAC value, these two shapes are very close to each other. But SDI, numerically, they're quite different. Now let me scroll down here. We already saw those. And now we're starting to see the second order show up in the 120. I got an order cursor on here. And the 60 frames per second says the running speed was 1460. Down here it says it's 1458. Probably within 1 delta F of the actual speed of the machine, which I didn't measure with a tachometer or anything. I'm just relying on the ODS-FRF, the largest peak in there, to show me what's going on in this data. So here we had what, 11,000. How many down here? 12,000. So quite a few, but we've only selected 10 of them that correspond to the X and Y motion of our 10 points of interest, where we're really interested in looking at vibration. Let's go to the last set here, 120 versus 240. Again, this is where scripting is really handy because it kind of rearranges everything, opens the correct windows, closes all the ones that we're not interested in. Excuse me. And so now we can see the result we saw in the PowerPoint, a lower MAC value and an SDI value that's a little higher. Again, let me scroll these down so we can see from the envelope what we've actually got in this data. Now the 240 is showing us actually the first 4 orders of the machine. And up here we've got 2 orders, so we can drag that cursor over there and drag this cursor over here, and now we're animating the second orders, 2900 RPM versus 2911, 2916. Something else to notice here though, and that is that this envelope down here looks a little fuzzy. And the reason is, what happened to me here? There we go. The reason is that these, the 120 and the 240 are what's called slow-mo or slow motion. And so the sample rate in the video actually changes as it's being recorded. And that will show up in the spectrum envelope here. So that 240 measurement that I made, I really should go back and do it again and do it more carefully, because what I'm seeing here is a little bit of, in the envelope, I'm seeing, well, let me scroll over here. You see right here, here's the running speed, and it's showing me actually 2 peaks in there, which means that some of the ODS-FRFs that are calculated out of the 12,000 actually had a different running speed in them. But you can see that from your data. Up here, I got nice clean data. If I zoom in here, let's just zoom in on this one. You can see just a nice clean running speed peak. And that is an envelope, it says up here envelope of 12,435 measurements that were extracted from the 60 or from the 120 frames per second. So we got a lot of tools here that allow us to improve our results. Let's move on. We got here, we're going to compare the 30 with the 60 frames per second ODS. So we already saw that in our PowerPoints. Let's go back and look at it in real life here. So now we've got the 2 PowerPoints. I had to do a calculation in the script to make sure that I had not the alias frequency, but the running speed frequency in this shape table of the ODS data, so that I could convert from mils to inches per second. So now we're comparing inches per second here with inches per second down here. And the SDI is more sensitive to the actual numerical values, and both magnitude and phase. Now the curve fitting has changed the phase of the ODS up here. I actually curve fit this ODS to the 60 frame per second ODS, and the phases line up such that the MAC value is 1 with a whole bunch of decimal points. So it's very accurate. Let's go look at the next one. This is 60 versus 120. Again, the curve fitting has lined up the phases a lot more accurate, and we'll look at them in a minute, but the magnitudes are way off still. Same shape, not good magnitude. Now, what is the answer for that? Well, maybe my scaling, when I took the data I could go back, reprocess these videos, be a little more careful with the scaling, the distance between 2 points in the video, and then the ODS-FRF calculation. We didn't get into all that about spectrum averaging and windowing and so forth. All those issues could affect the accuracy of our results, but these are good results. I mean, if I'm getting the same shape, the same ODS from every video, I should be pretty happy with that. It would be nice to have SDI match up perfectly. And again, that's saying that my numerical values of the magnitude and phase are exactly the same. Now you can just look at the numbers here of the two shapes and see that there's a little bit of difference between them. So the videos that the numbers that I extract from the videos are just not quite the same. Let's do one other thing here now. Let's just take this video or these two results, and let's do this. Let's go back. Let's go back to the 30 plus 60, because I've been through this before, so we'll do a little better on the results. Now I'm going to go here to the shape table, and I'm going to put up something called a complexity plot. So now I'm going to be able to look at the magnitude and the phase of this shape. And there you can see them all in they're just some vectors with phases, magnitudes and phases. I'll make this a little larger so it's easier to see. Let me do the same thing down here and we'll take a look at this. And complexity plot. Well, it looks like almost the same shape, but the phase is quite different. Now let's normalize the phase on both of these. So I'm going to go up here and display normalize the shapes. Bingo. What it did is it took all these phase angles, it took the magnitudes, retained those, took the phase angles, and with this little slider here where I can decide, how I want things to be. Here, they're all negative. If I slide it all around this way, they're all positive. So now they're all the phases are positive. So 0 and 180, that's interesting. Oh, it switched. I got to go back and change it back. Let's go. Let's see. Why did it switch on me? Okay, so now they're all basically 0, except for one that's on 180. Oh yeah, that one little guy there is sticking out at 180. Let's go down here and do the same thing. Now what happened to Mac? Mac stayed good. SDI is still, okay, let's see, display normalized shapes. So this took the phase and set them all to 0. SDI got better. It's saying that these two shapes are 60% alike. And their Mac value says that they're collinear. Obviously, they're collinear. They got 0 phase in each. So we're just looking at the magnitude of the numbers, and they still match up. That's pretty much all I wanted to show you. Mark, let's go back. I'll leave this up and we'll go back and we'll just look at the final conclusion here, and then we'll, if any of you have any questions.
Yeah, feel free to type those questions in now and we'll go ahead and get those answered. We got a few minutes left here.
I'm going to go down here to the conclusions and I'll just do a little more talking. But we've pretty much been through everything in these slides. So a cell phone is a low-cost, non-contacting vibration measurement device. Data can be extracted for machines running below 900, 1800, 3600, 7200. And as I say, you got to be careful. And if you got a peak showing up at less than the running speed, then it's been aliased from a higher speed. So if you sample with a higher sampling rate, FPS, then you're going to see the peaks of the machine. But this is good for lots of machines, lots of orders. Okay, we talked about the pixels being simultaneously sampled. Again, they are simultaneously sampled in a more expensive video camera, but you're talking $10,000, $20,000 for the camera, whereas you've got a camera right in your pocket. The video ODS, we looked at them in different ways. We can look at it in a time domain, a frequency domain, and it will show us where good spots are to put a triaxial Excel. We looked at time-based and frequency-based, and we looked at MAC and SDI as a numerical measure between two different shapes. And again, we differentiated from displacement to velocity. So we were looking at the shape values in velocity units. The advantage of the frequency domain is that you use algebra. You just multiply and divide. You don't have to do differentiation or integration using integration calculus. That's what you'd have to do in the time domain. But in the frequency domain, it's just algebra. So we do all the differentiation and integration in MEscope in the frequency domain. And then we can go back to the time domain if we want to look at it in that form. Okay, anything?
We did have a question here, not necessarily related specifically to video ODS, but Mark is asking, what would you say are the most major changes in recent versions of MEscope, more specifically from version 5 and onwards?
Gee, I don't even know the answer to that. Brian, maybe you can answer. All this video ODS stuff is relatively
Yeah, this is relatively new, certainly. Lots and lots of, well, boy, there's been lots of bug fixes, lots of enhancements. Version 5 is how many years old is that? That goes back a ways, right?
Yeah, version 5 was basically 2008, and
before this, yeah,
so you know, we've added things like the Polymax curve fitter, the AF Poly curve fitter. We've added, you know, 32 and 64-bit. Version 5 was when we went to 32-bit from 16-bit computing. Now we're at 64-bit, meaning we can access a whole lot more memory. SDI is a feature that's come out since version 5. The photo modeling came out right around 5, but we've improved on that greatly since then. Transmissibility chains have been added in. You know, they're version 5.
I would say is the ODS-FRF or video ODS.
Yeah.
Certainly.
Yeah, that's
certainly.
a whole complete new feature.
Yeah.
Yeah, yeah.
And,
sorry, go ahead.
Well, we're adding features. We added features last week, so we're fixing bugs and adding little features that maybe nobody notices. But MEscope is 30 years old, and we just keep adding features to it. So it's getting better all the time. And of course, you got to be on support to
Right.
get the latest features and the bug fixes.
Mm-hmm. Now, I did get another question here. Eduardo is asking, how can you avoid vibration from your hand when you are recording a video to analyze? That's a good question, Eduardo.
Good question. I have a little tripod here that I used. I set it on the tripod. There are a number of different tripods. You can actually buy a little attachment that will remove ground vibration or floor vibration from isolate the camera from things like that, so you're going to get a better video. We've got customers that are using MEscope on a ship, where the ship is bouncing around in the water and it's very difficult. Now, I didn't show you how to remove all the background motion, but we have commands in MEscope where if the video is just moving all over the place because of background vibration, typically, now your hand is going to be very random, so that's probably not a good thing to do, hold it in your hand, unless you've got a very steady hand. But you can remove all the background motion from the video, and what it does is it will take the background motion and subtract it from the motion of the part that you're interested in, the test article. So you get a much more accurate result, and we've done testing with that, and that works pretty well. But there's no substitute for actually.
Yeah, I mean,
go ahead.
Tripods are one thing. We also found that using a remote trigger also helps, so that you aren't touching the cell phone and moving it when you start and stop recording.
Yes, I use that to do these recordings, and it's, I don't know, $20 on Amazon for a little remote thing that you hold in your hand, and it talks to the cell phone and starts the video recording and then stops it. You just push a button. So that, now the other thing you can do, I showed you in the video, is if you don't have that, and when you touch the cell phone to start the recording, there's going to be a little bit of shake in the video at the beginning and then a little bit of shake at the end. So if you take maybe 30 seconds of data, which doesn't take very long, then go in and remove the first 10 seconds, the last 10 seconds, and just keep the 10 seconds in the middle, and that'll be good data to process. And when I showed you that the spectrum envelope for the 240 was a little fuzzy, that was an indication that my video probably had some different frequencies in the beginning or in the end of the recording. That now you can remove them in your cell phone. There's a little edit feature in the cell phone for the slow-mo feature, because the slow-mo does record at 2 different speeds, and you need to remove that either in the cell phone or in MEscope with the video wizard, and just don't use the beginning frames and the ending frames of your video, and then you'll be fine.
I did want to, before we wrap up here, just go through some pricing if anybody's interested. There's mainly 3 different ways that you can purchase video ODS. The first thing is what we call video ODS Assist, and if you just want to, basically dip your toe in the water, if you will, you can send us a video, we'll process it for you, and we'll send you both the time waveform and frequency, and send you basically back a video that's been processed in MEscope. Again, that's called Video ODS Assist, and that starts at $399. The second way to purchase Video ODS Assist is through our subscriptions. So we have monthly subscriptions for many of our MEscope packages. For Video ODS Assist, those start at $1,049 per month. if you want to go that route. If you just want to purchase a month or two, you can do that, and we'll just bill your credit card monthly. And the third way is our traditional way with perpetual license. If you already have MEscope, you can purchase the Video ODS Assist package for $6,600. If you're brand new to MEscope, you can purchase the whole shoot and match for MEscope with Video ODS for $12,000. So anyway, those are 3 different ways to purchase Video ODS Assist. If you have more questions, you can reach out to us at sales@vibetech.com, or if you have a local Vibrant reseller, you can get a hold of them and they can assist you with that as well. If you have any additional questions, feel free to reach out to us as well, sales related, and or if you have questions about the webinar, we'll be happy to answer any questions. With that, guys, I think we'll wrap it up. Any other last things to send us off?
All right. No.
Okay.
This is great technology. I certainly recommend that you get it. And the other thing I didn't mention, it's a complement to using accelerometers. If you have a route-based machine health program going on at your business, in manufacturing, petrochemical, or even a manufacturing assembly line, you've probably been using accelerometers for years and you trust them, you rely on them. But videos, we want to promote, and we think it's the right way to go as a complement. So you can use a video to see what's moving around, a quick look, maybe give you some ideas about where to put accelerometers you weren't even thinking about, or you can see vibration of parts that you could never instrument. For instance, we could never put an accelerometer on one of these rotors or even the shaft. Now, people have tried to do things like that, but it's very expensive and time consuming. So being able to use your cell phone, and as I mentioned, we offer a high-speed camera. It's going to cost you, double the price of MEscope to do that. We ship it as a kit with lights and tripods with stanchions for the lights and the camera. And then you can go up to a kilohertz or even higher sample rates if you're interested in higher frequency. But for low frequency, even, again, you have to be careful with the aliasing. You're going to have peaks show up in your spectrum that are aliased higher orders. And I mentioned that in our software, we can actually unravel the alias frequencies when we know what the machine speed is. And typically that's the highest order peak in the base spectrum. Once we know that, we can unravel. We have what's called an anti-aliasing order cursor. Now you saw the order cursor here in some of this data. This is just standard in a MEscope data block here, where we turn on the order cursor and bingo, it finds the peak for the second order. Now it's assuming that this is the first order, the running speed. So we do that, we go on and find the aliased orders the same way, and then we unravel the spectrum so you can actually animate the order-based ODS. And that's what we did with the 30 FPS. That ODS is valid even though the frequency is wrong because it's been aliased, but all the data for that ODS is correct. So with that, Mark, I have nothing more to add. Mark, are you there?
Yep, we'll go ahead and wrap it up there. Have an enjoyable summer, everybody. We'll get it on one of these webinars spun up here, and so stay tuned to your emails. With that, we'll let you go. Thanks, everybody.
Okay.
Bye.
Bye.